Welcome to Chem 106. Have you bring your exams back to the screen. And if I could have you try to do the difficult work of setting aside the exam and your feelings about the exam, gathering up your putting about this material. That is a hurdle, right? So I thought as a class that what's this? I thought as a class that you did well. I know that many of you felt confident and happy in how you did on the multiple choice. The actual score that includes the short answer is almost invariably low. Why is that? Some of it is because I tend to ask harder questions on the short answer so that I can give you partial credit. Some of it is the very nature of short answer versus multiple choice. Lots and lots of places just get things slightly wrong in Chem 106, right? And that includes everything from digits to how you express your math to what your units are. Those things don't always show up in a multiple choice, but they definitely show up in the short answer. It always puts me in a different position of having to take off points, which always hurts. Just be aware that if what you are writing is false according to the notations and assumptions of math or chemistry, I can't give you full credit. So occasionally it will happen that a student is trying to say, for example, the connection between the temperature that you run a reaction and the rate constant and the rate, right? And conceptually, the question is, or the connection is, when the temperature goes up, what happens to the rate constant? It goes up, right? And students like to say that that means that temperature is directly proportional to the rate constant. Actually, it's not directly proportional because the temperature is inside the E function, which is a different relationship than direct proportionality. So even though I know what you were trying to say, if you actually say something that is different than that, bad. I don't take all the points out. The other thing that I saw is that it's still difficult for you to always, as a matter of course, consider significant digits. And so if you have done your significant digits and reported your answer with the wrong number of significant digits, I do have to take off a certain amount of points. How come? Why is that? Why are chemists so obsessed with it? No. It's just because they're weirdos, right? I can tell you from a scientific perspective, scientists and chemists deal with measurements all the time. When I write a research paper and report a number, the number of significant digits tells me how well I know that number and how precisely I know that number. And so from a scientific perspective, reporting the wrong number of significant digits is actually reporting a different meaning. So that's why it matters. Now, you're in luck. I have to take off points for significant digits. How many points did I take off max for significant digits? Total on an exam. Half a point on the short answer, which then gets scaled by 2/3. So how many points did I take off? Not that many. Just enough to remind you to do it. Okay. Some of you have looked over your exam here. You're welcome to come and look over exams in office hours. That's actually a really great opportunity to go through and say, did I understand this correctly? Am I thinking about this correctly? did my exam pinpoint something that I can fix and how I understand things to make the rest of the class work better. I would recommend that you take the opportunity to go over the whole exam, not just the things you got wrong. Ben's laughing here. How come? Partly to review it. How many of you have had the experience?
One, to solidify what you already know, and two, you might have guessed right on something else, so.
Yeah, you might have guessed right, but that doesn't mean you would have to help to go over it. Okay, so you're welcome anytime to come over and look over your exams. I also, at the end of the semester, provide extended office hours, and I'll reserve a little conference room. So you can actually come and go over all of your exams. You can do it as a group. I'll have some blank exams for you to go over so that you can have the experience of taking the exam and consulting with me and consulting with the people around you about, were you guessing or did you understand why that was the answer? So that's pretty helpful. All right, let's start with a prayer. I start every lecture by saying this is practically my favorite lecture. Maybe not, but it's a good lecture. There's a lot of really key ideas. You can put all the ideas together today. We're going to use the ideas from today, from now until pretty much the rest of the course, which is great because you master this and you have a good feel for this and it makes sense to you. You will work with that for the rest of the semester. It's also a good thing because if you're still struggling with it, then what? Lots of opportunities to try to fix it. I have a volunteer to say a prayer for us.
So my Father, we give you Tuesday morning. It's like ministry, and we ask God to upon us that we can all hearts open. All those that may be sick or afflicted, that they can begin the process of healing soon.
By the way, how many lectures do we have? 14. So after today, we're almost halfway through. A little hard to believe, isn't it? Okay, so there's exam 2 is only 4 lectures, just like exam 1. So after today, we're halfway through the material for unit 2. And this is how unit 2 works. First 3 lectures are all foundational concepts, equations, and connections. The 4th lecture of unit 2 is, okay, you understand, now apply it to a specific system, which is solubility, and use what you know of the principles to predict and explain what happens with solubility. So we're more than halfway through the ideas. Lots of ideas. Last time we talked about equilibrium, right? And we have mentioned equilibrium starting from the first lecture. So turn to your neighbor and explain what you know about equilibrium. How do you recognize it? How does it act? What does it have to do with rates? What does it have to do with concentration? Okay.
The equation where the rate concentration. That I always get like. Yeah, exactly. So like
That's where the reaction needs to be.
Yeah, exactly.
I can't really see the one answer.
You got this, Jason. You got it.
So we started out the class about chemical reactions and kinetics, right? And we talked about what happens to the concentrations of starting materials and product as the reaction progresses. And we track that process by tracking concentration on the y-axis and time on the x-axis. We recognize equilibrium because that's the point at which which the concentration stopped changing, right? Okay, unit 1, we talked about the rate of that process, the rate of the forward reaction and the rate of the backward reaction. And what we said is the slope of the concentration versus time curve gives you the rate. And this, so if we take this curve, if we take the slopes of the curve at each time point and plot them, that becomes the red line here. If we're plotting the slope of the change in reactant concentration over time, that gives us this. Okay, so what we have is a situation where when we create products, those can back react to form starting materials, right? So at some point, what happens is the rate of the forward reaction equals the rate of the backward reaction. And when that happens, what must happen to the concentration? Stops changing, right? So the rate of the forwards and backwards reaction they equal each other, and the concentration. Okay, if we take an expression of a rate law for the forward reaction, and then we think about the same thing happening back, but in the reverse reaction, we can set the rates equal to each other. Set the rates equal to each other. If we rearrange those and put the forward rate constant divided by the reverse rate constant, that gives you a ratio of the concentrations of products and reactants, right? That ratio is what we call an equilibrium constant. So from now until the end of the course, we're going to keep on talking about the equilibrium constant. All right. What an equilibrium constant tells you is that for a given reaction, we know something about the relative amounts of product and starting materials when we get to that equilibrium position, right? Okay. We're going to do a lot of predicting what those concentrations are using equilibrium constants in a whole bunch of these ways. But I want you to explicitly recognize that the amounts of material you get at equilibrium actually comes from the kinetics. So we sort of talk as if equilibrium is a different set of rules and situations in kinetics. It's really not. We get to talk about them as if they're independent. But what actually happens? Okay, if you look at an energy diagram from kinetics, could we say that the rate constant forwards and backwards for that energy diagram, are they going to be the same? Where does the rate constant comes from what? It comes from the activation energy. And the activation energy is the difference in energy between a starting position and the height of the, what the energy is at the transition state up here, or what the molecules look like at the transition state. So if you looked at that picture, tell the people around you, what do you know about the energy of activation forwards versus the energy of activation for the backwards reaction?
Reverse reaction has higher reverse reaction has higher LWC.
What you can see is that the energy difference going backwards is a lot bigger than the energy difference going forwards, right? And you know from our Arrhenius equation that that means that the rate constant for the forward reaction is what? It's a higher value. Okay, which means that when it comes to equilibrium, the rates will only be equal if the concentration of starting material is lower. Let me draw that out. Actually, let's do that here. So let's do this one. This is an exothermic reaction, right? How do you know it's an exothermic reaction?
Energy is lost.
Okay, the potential energy of the products is lower, right? When you have an exothermic reaction like that, what do you know about the rate constants forwards and backwards always? From this diagram, you know that the energy of activation forward is lower than the energy of activation backwards, right? Which means the rate constant forward is greater than the rate constant backwards. Which means what? Means when you set the rates equal to each other for this particular diagram, the K forward, rate constant forward is greater than K reverse. And you know, when you set the rates equal to each other, that the forward rate is equal to, we'll do an easy reaction here. We'll assume it happens in one step. So there's a single peak like this. Starting material is A, product is B. So the rate forward is equal to the rate constant forward times the starting materials. And the rate backwards is equal to the reverse rate constant times the products, right? Okay, for this reaction, K forward is higher, and our K reverse is lower, right? In order for this equal sign to be true, what do we then know about the concentrations at equilibrium? You want to say it out?
Must be more products.
There has to be more products than starting materials in order for them to ever equal each other. So at equilibrium, the product concentration has to be higher and the starting material concentration has to be lower in order to make the rates equal. So because the energy diagram says that it's exothermic, when our product concentrations are lower, it will only come to equilibrium when the higher rate constant forward is compensated for by a lower final equilibrium concentration. So the kinetics and the equilibrium stuff, intricately connected. And they all come from the energy diagram, right? Okay. Do the same analysis. See if you can go through it for your neighbor. What will you know about the equilibrium concentrations just from looking at the energy diagram and the kinetics?
Lower. Activation energy is greater.
Means you're gonna have a little.
And
Or sorry. It's perfect.
Can you see how everything is connected? You understand what the energy diagram says about a reaction? That tells you a lot about the kinetics and the equilibrium, and they're all connected. Okay, so the principle here, and I want you to have just engraved upon your soul, is that every reaction has a unique equilibrium. So some reactions will produce a lot of product at equilibrium, some will produce not very much. You get a whole mix of all the possibilities. Okay, we have some terminology. If we come to equilibrium and we have a lot of product or more product than reaction, we say equilibrium lies to the right. Why the right? The product is usually written on the right. Okay, are there other wordings that we use to communicate the same thing? What are some other ways we say the same thing? We say it's product favored, right? If we end up at equilibrium, we have more starting materials than products, then we say equilibrium lies to the left or on the side of reactants, or we say it's reactant favored. Okay, now I want you to go from thinking about just what it looks like at equilibrium to the process of how a reaction gets from where it starts to the equilibrium position, right? And we can think about that process by saying, does what we have at the moment look what it will look like at equilibrium, right? If there's this unique equilibrium, what happens is, if you don't have enough product to have it look like equilibrium yet, what's going to happen? You're going to make more product, right? So you're going to use up starting materials to produce product. So which way is the reaction going then? Forward from where you start. Now, can I set up a reaction, a mixture of starting materials and products where I have too much product? Sure, you could. And if you have a reaction at a given time point that has too much product, then what's going to happen? The reaction is going to want to reach equilibrium, but equilibrium is actually to the left of the conditions you actually have. So what's going to happen? You're going to move backwards. Right? Okay, so we're going to do a lot of talking today about the progress of reactions, about reaction quotient, and different things related to that. But it's all based on the idea that every reaction wants to go to its unique equilibrium, and it'll do whatever it takes to get there. It's all connected. Okay, so if we have this reaction, hydrogen gas plus iodine gas, or I guess it's gas to produce hydrogen iodide. Can you draw a concentration versus time curve if you started with all starting materials? Draw a different curve, supposing that you started with all product. Can you track what would happen? And draw it. This is a lot of skills used at once, right? Good practice. You start with all starting material. Do you have enough product yet to be at equilibrium? Probably. Okay, so what direction does the reaction have to go? Forwards to the right. So what's going to happen to your starting material concentration? It's gonna decrease, right? Actually, it's going to decrease like this. What's going to happen to your starting material concentration? It's going to increase, right? Okay, if I start with all product, what's going to happen? I have too much product, so I'm past the equilibrium position, right? So what's going to happen? Reaction has to move backwards to reach equilibrium. So what does the curve look like? If I start with all starting material, my starting material is going to be used up to make product. I'm going to produce product. Okay, I told you that equilibrium lies to the right. What does this diagram have to do with the statement that equilibrium lies to the right? You have more product than starting material. If the equilibrium had been to the left, what would we know about these curves? This blue one would end up higher than the other. Okay, what is this curve showing? When the reaction starts, I have only product, and I start with zero concentration of starting materials. So the reaction has to move backwards. I use up a small amount of product, make a small amount of starting material. But does the reaction change concentrations very much based from its starting position? Why not? If you start with all product, you're starting with a position that's closer to where the equilibrium position is. So the concentrations don't have to change as much to get to the equilibrium. Okay, so here's a question for you. Oh, well, this is supposed to be hidden, so don't even ask. What's the answer? So we take the idea that a reaction can be described by where its equilibrium is, and that's unique for every reaction. How do we know where that position is? Well, we know that from the equilibrium position. That's what we use the equilibrium constant for, is to tell us, does equilibrium lie to the right and how far to the right? Does equilibrium lie to the left? How far to the left? And we can figure out what's going to happen to any reaction from any set of starting conditions by comparing what are the conditions you have to what are the equilibrium conditions as defined by the equilibrium. Okay, so how do we define the equilibrium constant? Tell your neighbor how we define the equilibrium constant, and then teach your neighbor some things about the equilibrium constant. You can pull that out of the foundations of the.
All rations of products.
And then all.
It's different than.
This.
Greater than one we know.
Well, this is what I would say about the equilibrium. First thing is, it's a big K, capital K, where rate constant is a small k. If you write an exam and you write small k when you mean big K, what will happen then? Everything that you write will have been made false. Please don't do that to yourself.
Yeah, my kids.
Okay, so K tells you, does the equilibrium lie to the left or right? And it depends on the temperature. By the way, why would it depend on the temperature? We can talk more about this next time. If we go back to our energy diagram here, the mix of products and reactants that you get depends on the relative energies of activation for the forwards and backwards reaction, right? What happens to the two, or which depends on the rate constant. So really, the ratio of products and reactants that you get depends on the rate constants, right? When you change the temperature, what happens to the rate constants? They change, right? Do we change the forwards and backwards rate constants the same amount when we change the temperature? Okay, Sam says no. How come?
Concentrations don't change, right?
Well, if we look at the Arrhenius equation, the energy of activation doesn't change with temperature, right? So the Arrhenius equation says the rate constants is equal to this, right? Okay, the energy of activation forwards and back is set by the structure of the actual molecules in the mechanism at the transition state, right? So we're not going to change the energy of activation when we change the temperature. What do we change when we change the temperature? We're changing the percentage of those molecules that have enough energy to go over that barrier, right? Okay, if the energy of activation is constant, change the temperature. What's it going to make the biggest difference to? Forwards or backwards reaction for this? Whatever has the highest energy of activation is going to change the most. It's going to, too many ideas in one sentence. Okay. We're comparing forwards and backwards reaction, right? When we change the temperature, it has the most impact on whatever direction has the highest energy of activation. When we change the temperature, we're selectively changing the K value that corresponds to the highest energy of activation, which means that we're changing the equilibrium constant. Remember that the equilibrium constant is the ratio of the rate constants? So if we change the numerator more than the denominator, do we get the same K value? No. So go back to here. When we change the temperature, we change one of the rate constants more than the other, forwards or backwards. And what does that do to your K value? It necessarily changes it. So every time you change the temperature, what do you do to your equilibrium constant? You change it. Okay, we're going to do some talking today about the direction of the change. And then in the next lecture, we're going to have you actually use equations to calculate what the new equilibrium constant would be based on the delta H value. Okay, take home message. K is magic. It tells you what the equilibrium position is going to look like no matter where you start from. Okay, so what are we going to use it for? If K can predict what equilibrium looks like, can we use the K value to actually calculate the concentrations that we get at equilibrium? Yes. And how good are you going to get at that? So good. Yeah. Okay. So I showed you this reaction. We said the equilibrium lies to the right. The actual equilibrium constant expressed in terms of concentration for this reaction is 64. So how far to the right is the equilibrium lie? Far, right? So if we start with all starting materials, most of our starting materials get used up, converted to product, right? If we start with all product, hardly any or only a little bit of our product gets used up as we move back. Okay, tell your neighbor. If you turn to the back of your Gilbert textbook, there are huge tables of equilibrium constants for different reactions, particularly for acid-base reactions. There's like Somewhere in the appendix, there is a table that's like 5 or 6 pages long for all the equilibrium constants for certain acid-base reactions. Where did we get those numbers come from? If every reaction will reach a unique equilibrium, can we just measure the equilibrium concentrations of the products and starting materials for any reaction and then use that to calculate our equilibrium constant? Yeah, we can. So one way we do this is we just measure the equilibrium concentrations and call it good. Now, there are individual instances where we don't want to wait for a reaction to come to equilibrium. Sometimes it's actually easier to use kinetic methods to measure the forward rate. That's often done, particularly for biochemical processes. Okay, we have some transformations that you need to know. Now, most of the time or often when we talk about equilibrium concentrations, we're talking like when a chemist says concentration, what do they usually mean? They usually mean molarity. And so most we have equilibrium constants defined in terms of actual molar concentrations. But in the gas phase, sometimes we use partial pressure. How many people remember seeing this before? That or mole fraction for an individual gas. The partial pressure of that gas in a mixture divided by the total pressure. Okay, is mole fraction another way to think about concentration? Sure. So sometimes instead of concentration, we use partial pressures, which means if you have a mixture of gases at a certain pressure, the pressure of each gas in that mixture is a measure of concentration. Okay, so sometimes we do calculations using the partial pressures instead of the molar concentrations. And you'll get different numbers for the equilibrium constant when you measure the partial pressures compared to when you measure the molar concentration. So the numbers are different. Does it matter which one you use? Well, yes and no. The numbers are different, so if I'm dealing with the equilibrium constant in terms of concentration, my calculations better be in what units? Moles per liter, right? If I'm using an equilibrium constant Kp, what better my numbers have to be expressed with what units? Some pressure unit, right? Okay, we did some transformations. Forward K values versus reverse rate values for net reactions. Okay, let's spend some time talking about calculations involving K. It's okay if you're not very excited about these calculations. Totally fine. They're a lot easier than you think once you learn how to do them. If I can do them, you can do them. There's this. Let me just put it into perspective for you. I am an organic chemist by training. It's not my initial language. You've already seen that I tend to make slight math errors that give you the wrong answer. That's just something that happens. I was uncomfortable enough with math that after I graduated with my undergrad and went out to graduate school, I had math class nightmares for maybe a decade. You know that dream where in your dream, you realize that you signed up for some upper division class and you just neglected to go to class? Anyone else have that dream?
Yep.
And then you realize in your dream that it's 3 weeks before the final and you have to somehow make it up. I always had those dreams about math. When I took my oldest daughter to tour universities to decide where she wanted to go, we toured BYU, and I actually stood in front of the Talmadge building and turned to my husband and said, "Is this building new? Because I don't remember it at all." What had I done? I wiped the entire experience from my brain because it was traumatic enough that even the building didn't feel like that was something I could think of. Okay, so I learned how to do these calculations. You can learn how to do these calculations. How do we do them? We use rice tables. And really, the rice table, you don't have to memorize how to do it. You can say, well, what's happening here? What's going on? Based on what you know about how reactions happen. Okay, so let's go back to our initial reaction that we've been talking about today. Equilibrium constant is 64. If the H2 concentration sub-zero, I2 concentration. What's that notation mean? Yeah, when we put a little subscript here, that means at time equals 0. Okay, so what is that telling us? We start a reaction with a starting concentration of 200 millimole of our starting materials, right? Okay, think about what's going to happen. Do we start with any product? No. Have we reached equilibrium from our starting conditions? No, why not? Well, we know from the equilibrium constant that's 64 that equilibrium involves a lot of product and we don't have any yet. So which way is the reaction going to go? It has to move forward. We're going to use up starting materials to make products. So if we think that through, here's our reaction. Here's our starting conditions, right? We know we're using up starting materials to make products. So what's going to happen over the course of the reaction is that our starting material concentrations are going to go down. Do you know how much they're going to go down? We're not pulling that number out of the air. We don't know off the top of our head. So we just say it goes down by a certain unknown amount, 1/6. And how come the hydrogen and the iodine concentration go down by the same amount? Stoichiometry is 1:1. So whatever happens to our hydrogen concentration, same thing happens to happen to our iodine. Okay. When we convert hydrogen to hydrogen iodide, what's going to happen? For every 1 molecule of hydrogen gas, we're going to produce 2 molecules of hydrogen iodide. So if the concentration of hydrogen goes down by X, the concentration of hydrogen iodide has to go up by 2X, right? Okay, so equilibrium concentrations are just what we started with, minus how much had to be used up to get to that equilibrium sweet spot, right? So this rice table, it just says what you already know. Okay. And these values in the equilibrium line, those actually represent what you would get at the equilibrium concentrations, right? So we can take those values and say, okay, this hydrogen iodide concentration is here, that's 2X. And the H2 concentration, that's 2 minus X, the iodine concentration is 2 minus X. Okay. Take stuff from the bottom line of the rice table and put it into our equilibrium expression that you already know how to do. Set it equal to the value of the equilibrium constant. This one isn't super hard to solve. How come?
Take the square root.
Yeah. You take the square root of this side. You take the square root of 2X squared. What is it?
2x.
You take the square root of 0.2 minus X times 0.2 minus X. What is it?
2 minus x.
2 minus X. Okay, so then solve. Simplify, do some algebraic manipulation, solve for X. I'm not going to show that all to you. When you're done, you come up with X is 0.16 molar. Okay, stop at this point. Does it make sense for X to be 0.16 molar? Equilibrium constant is 64. What do we know? Equilibrium lies to the right, which means we should end up with a good chunk of our starting material converted to product. Does that concentration, does that X value correspond to that? Well, we started with 0.2. We're going to use up 0.16, so a lot of our starting material is used up, right? That's a reasonable answer. And then the question asks for calculate the equilibrium concentrations. So you just calculate what the actual values are for each position in the bottom row of the rice table. Okay. When we're done, we end up with mostly product and a little bit of starting material. you do. Here's a question. How do you check those are the right values? Do you have a way to find out if you made a math error somewhere? What do you know about this equilibrium expression?
Is it equal 64?
It needs to equal 64. So if you did your calculations right, you take the equilibrium concentrations that you calculate, plug it back into your equilibrium expression, and what should it give you? 64. If it yields 6, what do you know? You did something wrong. Go back to the drawing board, check your math, see what you did wrong. Okay, here is a gas phase reaction. And what they tell you for this reaction, equilibrium constant is expressed with respect to pressure. Where does equilibrium lie? Pretty far to the left, okay? If we start with all starting material, what's going to happen? Reaction is going to produce a little bit of product with a little bit of the way to the right, and then what's it going to do? Stop. Okay, so when we're done, what will we end up with? Mostly starting material, teeny bit of product. Okay, so we set up our price table. Start with our initial concentrations. If they only tell you what the starting material concentrations are and they don't mention the product concentrations, what does that tell you? They don't talk about the product concentrations, that means it's 0. So in this case, they only told you your starting material concentrations, you can fill in 0 in. What's going to happen? Next line, change line. So something like this. Equilibrium, look at that. Okay. Now, take the values and your unknown expressions from your equilibrium line of your rice table, plug it straight back in to what your equilibrium expression should be, set it equal to the constant. So you end up with this. Now, can we take the square root of both sides here? So now we have to solve for X. So the first thing we have to simplify, and I've heard, what do you do to simplify? Use FOIL. And then you come up with an expression. Okay. So we have this value. Use FOIL. First outside, inside, last. You end up with something still pretty ugly. What do you do now? Take everything that's in the denominator, multiply both sides by that. So essentially, you're taking the opposite side of the equation, multiplying it by what's in the denominator on the other side of the equation. And simplify. Get that? Okay. You want to simplify. Then what you do, like once you simplify, mostly, you end up with your x squared on one side of the equation and everything else on the other. What you need to do is have all of your values on one side of the equation, set it equal to 0. So I take this 4x, subtract everything else. With that, so we can insert. Okay. Does that help you solve for x? Yes, what you have done is set up a second order polynomial, right? Or a quadratic expression. And you learned in high school algebra that you can use the quadratic formula to solve for x in that case. This is what it is. So what you've done is set up a constant times x squared plus another constant times x minus another constant. And according to the quadratic formula, those constants are a, b, and c. You just take those constants, plug them into the quadratic formula. What does the quadratic formula yield? 2 different numbers, right? One number gets from using the plus sign, one number you get from the minus sign. How do you know which one is the right one? Can I promise you that you will always know? I can. Yeah, because you will find as you do these calculations that one of the x values will be negative, which would mean the reaction would have to move backwards when you know the reaction is actually going to move forward. Or one of the X values will actually be a higher concentration than you started with. So if you just look at the numbers, you know that one of them will not be possible. You can cross it out. If you're willing to think about what the numbers mean, you will never have a problem figuring out what your actual solution should be. Okay, so if we use a quadratic formula on that stuff back here, I end up with X equals 6.428 times 10 to the minus 4 atmospheres, which means, is it reasonable? Is this a reasonable X value? Does the X value tell you how much of our starting material gets converted to product? Just a little bit. Is that what we should expect? Absolutely. So we look at the number and we say, okay, well, that's a reasonable number. We use that number to calculate our equilibrium concentrations by subtraction. And then once we have those equilibrium concentrations, how do you check your answer? Plug it back into your equilibrium constant expression and see if you get the right number back. Okay, is that ugly? Yes. If you do it right, will that expression always give you the right answer? Yes. If you're like me, and more lines of algebra does not bring you personal joy and satisfaction, what options do you have available? One option is that you buy a slightly more expensive calculator that will solve the quadratic formula for you. Any programmable calculator, you can program it to solve it. You have a fancy calculator, it might have that built in. Now, I don't have a programmable calculator, and I just always end up solving. You can do that, that works fine, yes.
So how would you, like, once you graphed it in a calculator, how would you find, like, what would it be? Like,
I'm assuming that you'd have to have some quadratic formula function, and it would ask you what's your coefficient for A, what's your coefficient for B, and you put it in, and then it would spit out the two values. Since I don't have a calculator that does that, I'm just guessing. Anyone want to offer some insight here?
I had to like look online to find out how to like program it by
Yeah.
myself.
It can be kind of a pain in the bum to program it. So, yeah. Okay. Here's another thing for you though. Chemists are nothing if not eminently pragmatic. I'm about to show you that as much as you think you have hated significant figures, they are your friend. Okay. Back to here. 6.428 times 10 to the minus 4 atmospheres, right? How many significant figures do we have in our starting concentration? 2. If I subtract this number with 2 significant figures and subtract 0.0006428 and then round back to the number of significant figures that I started with, what do I get? Let me show you. Okay, so what we have here are starting concentration of our nitrogen equals 0.79 atmospheres, right? Equilibrium concentration is 0.79 atmospheres minus 0.0006428. Want to tell me what number you get when you do that? Equals 0. Read me all the digits. 6. 7, 8. What are all the other? Read me about 6 digits that you're calculating.
935.
935. Okay. Atmospheres. Do I really have 0.78935 atmospheres? I can only report that final concentration to 2 significant figures. So when you round back to 2 significant figures, what do you get? That 0.79 atmospheres. Okay. So what that means is when your X value is really small, I'm doing, let's see, In my equilibrium expression, if my X value is really small, this equilibrium concentration of nitrogen, can we tell the difference between the equilibrium concentration and the initial concentration? Can't. So what happens to our math if we can pretend that the equilibrium concentration might as well be the initial concentration? What do we do then? So go back to the math. Okay, so this math is ugly. Let me show it to you. What we had here is our KP equals we got an ugly polynomial expression because we had to carry through all of this stuff, the X is in the denominator, right? If we say X is very small, then that means 0.79 minus X is pretty much or approximately equal to 0.79, right? And we can also say 0.21 minus X within the limits of the significant digits might as well be 0.21. Okay, if we do that, what happens to our expression? Our number. Okay, how easy is this to solve? It's way easier. You multiply these through, you carry them through on the other side of the equation. You end up, what we get is 4x squared is 1 times 0.79 times 0.1. So what's our X value? X is the square root of all of that divided by 4. Is that a lot easier to do? Okay, so one way that you get to simplify your life and the angels begin to sing and you can now see the sunshine instead of only the clouds is to look at the value for the equilibrium constant. Now this equilibrium constant was 1 times 10 to the minus 5, right? So what did that tell you about how far the reaction is going to proceed forward if you start without starting materials? Hardly at all. And so then you can look at the significant figures and say, I think it's not going to actually make a difference to my, I can pretend that my starting concentration is sufficiently close to my equilibrium concentration that I can neglect that in the denominator when I do my math. How do you tell if that was okay to do? Are you guessing? Check if it was an okay thing to do.
Plugging concentrations back into the-
Yeah, do it the easy way by neglecting X in the denominator, which you can do when your K value is really small. That'll give you some concentrations, right? How do we check to see if those concentrations are good enough? You just plug them into the equilibrium expression, and if they're good enough, you get the right value. If that wasn't good and you don't get the right value, what do you do then? Then you can go back and do the quadratic formula. But as long as your K value is really small, you can assume that it's worth trying to solve without the quadratic formula first, and then check your number. Okay, so tell your neighbor which of these is an appropriate answer. This would be an inappropriate test question. It's not completely clear that all of them are wrong, right? What's the thing that you really care about? What you really care about is in your expression, you're gonna be adding or subtracting from a number, right? And as long as the X value you think is gonna be so much smaller than what you're adding or subtracting it from, that it isn't gonna matter within the significant figures, then that's when you review. However, that usually happens when you're not making very much profit. Now, different textbooks give different rules of thumb to help you guess whether you can neglect X or not. And I've heard everything from if your K is 200 times smaller than your equilibrium, than your initial concentration, then you can do it 100 times smaller, 400 times smaller. Really what you want to do is just guess and then check if your guess is correct. Let's see. How about this one? I've done one like this, almost the same one that we did. So we have fluoride ion reacts with water with a certain K value. What do you notice about that K value? Where does equilibrium lie? To the left. Are we starting with Taylor product or a mix? First thing to do with that is write the reaction, right? Because that helps you think. If fluoride, which comes from sodium fluoride, is our starting material. Do we have any product when we start? No product. Okay. What's going to happen in this reaction? Where's the reaction going to move from the starting conditions?
Very forward.
Going to move forward. How much forward? Not very much. So what are you going to try first? We're going to try ignoring the X in the denominator when we do our calculation, right? So we say this is what our reciprocal looks like. There's our equilibrium expression. We can solve for X, but actually, we can solve for X by doing X squared divided by 0.15. That's an easy algebra. Right? So then we get X squared equals a number, take the square root of that number, and that gives you your concentration. Okay. So there's a couple of things to remember, and then I'll let you have a break because you're probably internally weeping that you're still here and not watching the voice for a minute. Okay. So there's a way that what will always work. Can you always solve with the quadratic formula? Assuming that you end up with a polynomial expression, the quadratic polynomial, then you can always use the quadratic formula. But there's some things that make it easy. One is sometimes you end up with the square root, both the numerator and the denominator, you can take the square root of, then you set it equal to the square root of the expression. That makes it easier. You end up with a polynomial function, you can always use the quadratic formula. But if the K is very small, then you can neglect X from whatever you're subtracting it from or adding it to, and then you don't have to use a quadratic formula. There is another simplifying thing that we can use, but I'm not going to show it to you till the next unit because I want you to be comfortable enough with this. I think it's cognitive overload to layer on more things. Okay, take a break. I'll go pick up the recitation. I sent the print request, but accidentally emailed the lecture slides, so that's it. More modeling of different reactions. I really like this website. Step by step, it goes through very slowly. Okay, here's a question. You haven't had to do this kind of problem before. You have this reaction, sulfur dioxide reacts with oxygen to form sulfur dioxide. You have an equilibrium constant, AP, because we're dealing with gases, so probably they're expressing particle pressures. Tell you, you start with a closed container, like you'd run a gas phase reaction in. What do we start with? What's your rice table going to look like? Have any starting material in our original conditions. No, we start with all product. So what's gonna happen? Has to move backwards to reach the equilibrium, right? So you remember all reactions proceed towards equilibrium and start here. So if we start with all product, reaction has to move backwards to get to equilibrium. And you knew that if we started without starting material, reaction has to move forward. This one, the reaction has to move backwards, right? We could set up a Rice table for this and do the calculation, having assumed that it moves backwards, and we'll end up with an appropriate value for X, and you would solve it just like you would for a regular Rice table, except I'm going to say minus X for your starting materials in your change column, plus X because that concentration is actually. Okay, we can do those. The question that I want you to consider is, how did you know you had to move backwards? You can say, I had too much product. Okay. Start with all product. Chances are you have too much product. So the reaction has to move backwards. But I want you to think about the idea of asking yourself, from where I am at the moment, have I reached equilibrium yet? Or do I have not enough product? Or do I have too much product? So this idea of the reaction quotient Q that the reading talked about is just a way of asking, do I have too much product? Do I have not enough product? Which way will the reaction move? Okay, so Q, calculate it and express it just like you did for K, right? Instead of knowing that you have the equilibrium concentrations, Q is calculated using the concentrations at a given time point. So Q asks the question, with what I have now, if I calculated what would be an equilibrium expression, do I get the equilibrium K value back or not? Okay. So suppose I'm not at equilibrium yet. Will Q value equal the K value? No. If my Q is smaller than the K value, what does that tell you about these concentrations? Q is smaller than K. That means either the numerator is too small or the denominator is too big, right? What does that tell you?
It's going forward.
It has to move forward to reach equilibrium. So if Q is less than your K value, what do you know? At that moment in time, you're not at equilibrium, and which way is the reaction going to move? Forward to reach equilibrium. Okay, now suppose I calculate a Q value for a reaction at a given place or time, and my Q is too big, bigger than the equilibrium constant. What does that tell you? Well, if it's too big, either the numerator is too big or the denominator is too small, right? So that tells me I have too much product and or not enough starting material. So which direction is that reaction going to move? Going to move backwards. Okay, does that mean that by calculating Q, you know a lot? It does. So well, let's do this. Let's get this one. Go to this. So you had on the recipe or on the quiz, have this question number 9. A lot of you in your feedback said, go over this question. Okay. So here's our reaction. A plus B goes to 2C. Obviously, those are real reagents, but we're just using letters to represent them. And the question said, you start with 2 moles per liter of everything. What will your final concentrations of the starting material A be at equilibrium? Okay, think about what the question and the choices are actually asking. If at equilibrium, you end up with less than 2 moles per liter of your starting material, which way did that reaction move to reach equilibrium? If it's less than 2, are we using up A or producing A? Producing A, so the reaction moved to the right. Okay, when would we see that happen? That would happen when we don't have enough product yet. It would happen when Q is less than the K value. If the final concentrations of A are greater than 2, what does that tell you about which way the reaction moved to reach equilibrium? Backwards to reach equilibrium because we're actually making more starting material. Okay? If the equilibrium concentrations are 2, what would that mean? It's already at equilibrium because the reaction doesn't move forward or backwards. So we're already at equilibrium or we stay there. Okay, so how do we do that for this problem? First thing we have to do is figure out what is the equilibrium expression. We calculate the equilibrium expression and we do it the same way for Q, right? What would it be? So we take our product concentration and square it, right? We divide by starting material concentrations, each raised to the first power. Okay, and what do we know about that value? I don't remember, I didn't write it down. Let's suppose the actual number, let's suppose it's 4. Okay, what's our Q value here? Take the concentrations that we have, which is 2. Concentration of C is 2. Square it. You divide by 2 times 2, what do you get? Q is 1. If Q is 1, what do you know? I don't have enough product yet. So which way will the reaction move? To produce product. So what will happen to my starting material concentration of 2 molar? Starting material will be used up as you proceed forward. So what will your final concentrations be? Less than 2. Okay. So the Q value, compare it to K and it tells you, are you at equilibrium yet or not? And what's going to happen? Okay, so if Q, tell your neighbor, if Q is less than K, what does that mean? And see if you can connect it to the G.
Forward.
Q is less than K. We don't have enough product yet, so what's going to happen? You're going to move forward. What does that tell you about the sign of delta G at that moment under those concentrations? It has to be negative, right? So just by comparing Q to K, you figured out which direction the reaction will go and what the sign of delta G is at that point. Remind yourself, when a reaction is moving forward, what's the sign of delta G? Okay, when the reaction is at equilibrium, what's the sign of delta G? 0. Why is it 0 at equilibrium? Because the reaction is going to stay there, so delta G can't be positive or negative. If the reaction needs to move backwards to reach equilibrium, while it's moving backwards, what's the sign of delta G? It's negative for the backwards reaction, which means what for the forwards reaction? Positive. So we would say that's a positive. If we say that the reaction is moving backwards, then we say that's a positive delta G by convention. So whatever way we have the reaction written on paper, we assign delta G relative to the reaction the way it's written. So a reaction that's moving backwards has a positive delta G for the forwards reaction. A little convoluted, but okay. Okay, when Q is greater than K, what does that mean? What do we have too much of? Product, so what's gonna happen? The reaction will move backwards. So what's the sign of delta G? Positive. Okay, Q is equal to equilibrium. What's gonna happen? Shift in the concentrations. The reaction is not moving forwards or backwards. So what's delta G? Yeah, okay. So what we say is that for any given set of conditions, when we compare the Q value to the K value, that tells you what direction the reaction will move. So if Q is less than the K, we'll move forward. If we have a larger Q value than the K value, okay. What does that say about what happens to delta G over time? When a reaction is moving forwards, what happens to delta G? It starts negative As it moves closer and closer to equilibrium, what has to happen to it?
Zero.
It has to get closer and closer to zero. So over time, delta G changes as a reaction is progressing. If it's going forward, we start negative, we get less and less and less negative until we get to equilibrium. And at equilibrium, what's delta G? Zero. Okay, if we start with too much product, Q is greater than K, right? So we're over here on the right. Equilibrium is to the left of the concentration conditions you have. So what's going to happen over time? Which way's the reaction going to move? Backward. So tell me what happens to delta G over time.
Goes down.
Gets less and less positive until we finally get to the equilibrium concentrations. And then what? Delta G is zero. Okay, so does that mean that there is a unique and unchanging value of delta G for any reaction? No. It means that the value of delta G reflects the concentrations you have for that reaction as it moves towards equilibrium. Now in Chem 105, we had you calculate a number that was kind of like delta G, that was a constant for each reaction. What was it? It was delta G naught. Delta G and delta G naught are not exactly the same things. We'll talk more about that last time. Okay, K is 22 for this reaction. If the measured concentration of our starting material is 0.1 and the concentration of our product is 2, are we at equilibrium yet? What's the calculated Q value at these concentration conditions? Okay, so we have 2 divided by 0.1. What value do you get? Q is 20. Are we almost equilibrium? Yeah. What side of equilibrium are we on? A little bit to the left. So the reaction is still going to move forward a little bit to reach equilibrium. What do we know about delta G?
Negative.
It's negative. Is it huge and negative or small and negative? It's small and negative because we're almost to equilibrium, but not quite there yet. Okay, do this one for your neighbor.
Sorry, can you
Actually did with that. Let's do that.
with the -3? Yes.
What Q value do you get when you plug the concentrations into the experiment? So the K value and the Q value are both going to be defined as the product concentration times the product concentration divided by the square of the starting material concentration, right? So if they're all the same, what Q value do you get? 1. What does that tell you about where you are relative to equilibrium? Too far to the right. There's too much product, right? So what's going to happen? It's going to move backwards. How far backwards is it going to move? 20 ways, right? So tell me about the delta G.
Positive.
Positive, yeah. Okay. So tell your neighbor what happens to delta G as a reaction proceeds towards equilibrium.
Yeah,
Whether that becomes positive or negative.
Yeah. So in the direction that the reaction is actually proceeding, delta G starts negative and approaches 0, right? Okay, so if because it's the class that you're in, we have to talk about it in words. We're going to connect it to equations, and then you have to draw a graph that visualizes, right? Okay, so what's your graph? Delta G versus time. Have A goes to B. A is our B concentration over our A concentration at equilibrium. 10. Okay, if we start with all starting material, what do we know? What's our Q value if we start with all starting material? Trick question, it's an undefined number, right? What do we know about Q versus K if we start with all starting material?
Q value is smaller.
Oh, it's not undefined, it's zero, isn't it?
Yeah.
I'm doing it, I'm flipping it in my head. If I start with all starting material, what's my Q value?
Oh, 0.
Okay, so all starting. So if we start with all A, Q is 0 over whatever we start with, right? So Q is 0. So what happens to our delta G over time? At equilibrium, what will our delta G be? Be 0, right? So how do you go about drawing this? You say, oh, at equilibrium, it's going to get to 0. Once it gets there, will it stay at 0? Once reactions get to equilibrium, do they stay there? Okay, so over time, once we reach equilibrium, we're going to stay there. Delta G will be 0. How do we get there? Let's start. Sarah has it. She's doing the hands. Yeah, we start negative, right? So we start less than 0. We gradually approach 0. Okay. If we start with all product, what's going to happen? Reaction's actually going to move backwards, right? But we've drawn it forwards. So for the forwards reaction that's moving backwards, what happens to delta G over time? It starts positive. So this is the forwards. Starts positive and moves backwards. Okay. Trick for you. It's actually going to be important. Now, delta G, what does that mean? That means the change in the total Gibbs free energy, right? Turns out to be the change that we care about, not the absolute values. A graph of the absolute value. G versus time. We're plotting G versus time instead of delta G versus time. How are they connected? Remember when we plotted change in concentration versus time? We plotted concentration versus time, right? And the rate is the change in concentration versus time. How are those two things connected? By the slope, okay? So if we're plotting help if I actually had my slopes drawn correctly. This plot, what does this say? This plot says the G value is decreasing over time, right? When the G is decreasing, what's the sign of delta G? Negative. So the slope on the G versus time curve, it's a positive slope or a negative slope, gives you the delta G value. So the slope of this curve equals the delta G at a given time. Okay, notice, does the slope change over time?
Yes.
Yes, that's because the delta G changes over time as you approach equilibrium. Okay, do we care about the actual value? So the delta G plot, it ends up at equilibrium, delta G is 0. Is this at 0 G? It's actually 0 slope that matters. So this could be, could end up at 12,300 joules per mole. We don't care what the absolute value of G is, because that doesn't make the reaction go forwards or backwards. What we care about is how G is changing. So it's the slope of this curve. Okay. Explain to your neighbor the connection between the G and the delta G plot compared to time on the x-axis. And then we're going to move on to a new plot, which might blow the top of your head off, but actually explains everything.
Looking at that.
Yeah, that's right.
It's just like one
Actually.
Days and time.
So that means
Then like equilibrium could be like the energy is at like 1,000.
So these plots of G and delta G over time
Stays the same.
actually saying over time, the concentrations are going to change to reach equilibrium, right? So both the delta G and the G versus time plots are telling you what happens to those values as you approach equilibrium, right? But it's using time as the axis that tells you what happens as you approach the equilibrium concentration. And what we know is when a reaction is moving forward, delta G is negative. So as we approach equilibrium, moving from left to right, delta G starts negative and becomes less negative until we approach delta G equals 0 at equilibrium. On the G versus time plot, we see that because we get to a horizontal line where the slope is 0, which means the delta G is 0. And we could extend that time out 1,000,000 years, and what would happen to the plots? Once we reach equilibrium, what's going to happen? Stay there. Does it matter how long we wait? Are we ever going to move equilibrium? Unless we haven't changed the temperature or added something to the reaction, once we get to equilibrium, what's going to happen? Stay there forever. It probably isn't necessary to extend it out that far, right? Okay. What if instead of time on the x-axis, we had something on the x-axis that represented some measure of concentration? Okay. So let's construct a curve. It starts at the origin, the left-hand side, at 100% starting material and 0% product, right? Reaction proceeds as far as it is theoretically possible. Where does it end up at the other end? Wouldn't we end up with starting with all starting material? Where's the opposite from that? All product, okay? So at the other end, we would say it would be 100% product, 0% starting material. One way of presenting that is to say the extent of reaction. You have 100% starting material, the reaction has proceeded forward, that's 0 point, right? 100% would be the other end. Sometimes that's written as the extent of the reaction is 1, meaning we have 100% conversion of starting materials to products. Okay, so the x-axis here reflects progress of starting material towards conversion to 100% product, right? Is that sort of just a way of saying how far can the reaction proceed? Work. Okay. Now the y-axis is G, Gibbs free energy, instead of delta G. So is this kind of like the G versus time curve? Except instead of thinking about it progressing over time, we're thinking about what are all the possible values of G or delta G for every percentage of starting material and product. Kind of what we've been talking about, right? Okay, first question. What does the slope of the plot represent? Delta G. Okay, the slope of a plot represents how fast it's changing at that point. So if we have G on the y-axis, then the slope of that plot is delta G. Okay, so look at those plots, those two different plots, and tell your neighbor, does delta G change with the percentage of starting material and product that we have? You already know that was going to happen? Because you already know that the percentage of starting material and product tells you, are you at equilibrium yet? Are you past equilibrium? Are you at equilibrium? And those are going to come with different values of delta G, right? So this plot, we read it as saying the slope at a given point tells you roughly what the magnitude and the sign of delta G would be for a given percentage of starting material and product. Okay. What does this minimum point mean? What's the slope right at the minimum? 0. So that means delta G occurs, right? Delta G 0 is there, right? What does that tell you about the condition of equilibrium? Is it more starting material or more product? More product. So what kind of K value are we talking about here? Yeah, K value greater than 1. Okay, now watch what happens. What's the value of Q everywhere to the left? What are the values of Q everywhere to the left of that equilibrium minimum? Less than K, right? So everywhere to the left of that low point means you don't have enough product yet, right? So everywhere to the left of that point means Q less than K. What's the slope of this curve everywhere Q less than K? Negative. Okay. Everywhere to the right of that minimum point, what do you have too much of? Product. So what's Q compared to K for everywhere to your right of that point? Q is greater than K, you're past equilibrium. What's the slope? It's positive. Okay. So now pretend that you set up a set of starting material concentrations and you set up a certain concentration of starting materials and products. If I start here, where's the reaction going to proceed? Fall down until it reaches equilibrium, and it's going to stay there. Suppose I start with a set of concentrations up here. What's going to happen? Delta G is only negative for the backwards reaction. We have too much product, we're going to go back down to equilibrium. So does that plot actually summarize in one image everything that you already knew about how the reactions work? Yes. So what I want you to do is to get used to seeing this kind of plot and using it as the image to summarize how all the ideas are connected. Now, for some people, thinking in terms of plots and images and graphs is really easy and helpful. For some people, maybe that's not your first way of thinking about it. Useful. Okay. Predict a K value for this plot. When it comes to equilibrium, what's the fraction of product and starting material that we have? It's like 80% product, 20% starting material. What kind of K value are we talking about? Pi. Let's make one. Well, actually a K value of about 4. 4 times the amount of product in the materials, right? How about this one? K value going to be greater than 1 or less than 1? K was 1, where would the minimum be? So this is a K value less than 1. What percentage of product and starting material do we probably have? Maybe 20% product, 80% starting material. What kind of K value do we have here? About 0.2, 0.25, somewhere around the corner. So actually, this contains a lot of it. Okay, does this plot and the ideas of what happens to delta G over time as a reaction approaches equilibrium, does that tell you that there is a connection between Q and K and delta G? What's coming next? An equation. Of course, there's an equation, right? Oh. This is the equation. The delta G for any set of concentrations reflects the difference between Q and K. And calculate that according to minus RT times natural log of equilibrium constant plus positive RT natural log of Q. Now, I don't know if you remember, last time we talked about how delta G naught equals minus RT times natural log of Q. So we can also write the equation that uses the delta G naught value instead of all the things spelled out. And we're going to talk more about that next time. Mathematically, if you read that, when Q is less than K, what is the sum going to be? Negative. Did you already know that? Sure. Does the equation just say what you already knew? Yeah, is that a trend in this class? The equation summarizes what the concepts are? Sure. If you have too much product, then Q is gonna be greater than K, right? What will the sign of delta G be? Positive. Did you already know that? Yeah. Can you see problems coming where you actually have to calculate the values, actual numerical value and sign in kilojoules per mole? Sure. Yes. Okay. How do we have any control over the equilibrium? Do we get to tell a reaction what its K equilibrium value should be? We don't get to go to the bench top and set up a reaction and say, oh, chemicals, please, I need a lot of product today. Please, 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 can you change your K value for me? Does that work? No, but there are things we can do to trick the reaction into producing more product or less product by taking advantage of the relationship between Q and K. Okay, so this reaction says delta G is negative whenever Q is less than K, right? Or a reaction will proceed forward whenever Q is less than K, right? Can we set up a reaction to help Q be less than K? Change the conditions to make Q be less than K? Actually, we can't. So watch this. So we can change Q on purpose. Okay. If we add more reactants, does that make Q, that's going to change Q, right? Does it change K? He's already set, it's a constant. But if we set up a reaction and we actually change the concentrations we have, we add more reactants, does that make Q go up or down? If we add more reactants, what are we making bigger, the numerator or the denominator of the Q expression? The denominator, so what happens to Q? We make Q smaller. When Q is more smaller than K, what happens to delta G? It's more negative. So what happens to the reaction? Cause it to want to move forward more. Okay, so when we add more reactants, what happens to Q? It goes down. What does that mean in terms of how far we are from equilibrium? If we add more starting materials, what does that say about how far the reaction then has to move to reach equilibrium? Farther. So how does it respond? Responds by making more product on its way to reach equilibrium. Okay, if we add more product, what happens to Q? Bigger or smaller? Bigger, because remember products are in the denominator of the Q. When we add more products, what's that gonna do to Q compared to K? It's gonna make Q more bigger than K, or bigger than K if it wasn't there already. How does the reaction respond to that? Shift backwards. So if we add more products, we can actually make the reaction move backwards. Okay. Here's a question for you. What if we figured out some way to just keep taking product out as we want? I suppose the product was in the gas phase. You could collect it as it bubbled off. As the reaction proceeds forward in time, will the Q value ever reach the K value? It won't. So what happens to the reaction? It keeps on moving forward until what?
More.
Until you use up all starting materials. So you haven't changed K, but do you have control over what happens in the reaction? Yeah. So the K value is set. We don't get to change that for a reaction at that temperature, but we can play with that. Take it down. Okay. The idea of how what we do affects how much product we get, really an expression of the relationship between Q and K. But long before the thermodynamic principles of equilibrium constants and delta G were recorded, chemists knew what would happen to a reaction when you tweak something. So they didn't understand the fundamental theoretical foundation for it that you now understand. but they knew it would happen. This is a picture of Chatelier, French chemist. Lots of early famous chemists were French. Okay, and he said, if you have a system at equilibrium, so you let a reaction come to equilibrium and then it's at equilibrium, you apply a stress to the system. What does he mean by a stress? If you change something and push on it in some way or the other, what will happen is that the reaction will respond essentially by moving away from the stress and establish a new position. Okay, so push on one side of the equilibrium and you push the reaction towards the other side. This is just a description of what it looks like. It doesn't explain the theory. What we're actually doing when we make a change is we're either changing Q or we're changing K, right? If you change either one of them, does that change the difference between them? Which changes which way the reaction will shift. So anything we do that changes Q is going to push a reaction one way. Anything we do that changes K. By the way, what can we do to change Q? Change the concentration. What can we do to change K?
Change the temperature.
Change the temperature. Are those the only choices? All of the changes that we can make really are some versions of those. Okay. So here we have a reaction. What does the equilibrium expression look like, by the way? Equilibrium K equals, what's in the numerator?
Carbon monoxide.
Carbon dioxide cubed. Okay, include this. What's in the numerator or in the denominator?
Carbon monoxide.
Carbon monoxide cubed. Okay. So this is the reaction. If we take out carbon dioxide, what are we doing? What's going to happen? We are decreasing this concentration. So how does the system respond? It wants to increase the concentration to compensate. So what happens to the reaction? It's going to move forward. Okay. If we add carbon monoxide, what's going to happen? We're increasing this concentration. How does the system want to respond? By decreasing that concentration in response. How does it do that? Moves the reaction forward. Okay, what if we add iron oxide? When we add iron oxide, are we changing Q or changing K? Neither, right? Because it doesn't show up in the Q or the K expression. So does it make any difference? As long as we have some iron oxide, we're not completely out of it, then adding more makes no difference. Yep. Okay, for gases. This is the part, the comments that you gave me on the reading quizzes were like, explain what gases have to do with anything and what happens, right? For most of you, what happened is that you did gas law and ideal gases at the end of 105 when you were already so overwhelmed and so exhausted that you learned just enough to not get every answer wrong. And then what happened? They sort of drained out of your ears over Christmas break. Semester end. That's totally fine. Okay. Thing to know, if we increase the partial pressure, what that means is we're increasing the mole fraction of that gas, or we're increasing concentration. So increasing pressure is the same thing as increasing pressure. We're just expressing it in terms of units of pressure instead of units of moles. Okay, why increasing volume is like decreasing concentration? We have a gas in a container. It's going to occupy a certain space, right? If we increase the volume, what happens to the number of moles per liter? The liters got bigger and the moles didn't change, then the moles per liter went down. So increasing volume is like decreasing concentration. Okay, if we decrease the volume, what are we doing to how packed in those molecules are? Increasing it, so isn't that like increasing the concentration? Yeah. So the gas, if you relate it back to concentration, it's not that hard. Okay, sometimes there's things about inert gases. If you add a gas to the mixture that doesn't show up in your equilibrium expression or your Q expression, do we care? No. Because the relative, the ratios of the pressures of what's left relative to each other isn't going to change. So inert gases don't make a difference. Okay, so back to this reaction. If we add carbon dioxide, what's going to happen? We're adding starting material. That makes Q bigger than it was before. Sorry, I said that wrong. If you add starting material, what happens to Q?
Small.
It gets smaller. What does that do to the reaction? Makes it want to move forward. Okay. If we add whatever you call this ugly thing, product, what's going to happen? It is a product, but does it show up in our Q expression or K expression? So what happens? Nothing. If we increase the volume, if we increase the volume, does it do anything to our amounts of products? If you increase the volume, does that change how much solid or how much liquid you have? No. But if I increase the volume, what does it do to the selectively going to change your
So number 2, why does that not show up in the Q or the K value?
this is a solid. It doesn't show up in our equilibrium expression. It doesn't show up in our equilibrium expression. What is our equilibrium expression here? A equals 1 over the ammonia concentration squared, and also in the denominator is the carbon dioxide concentration. So if you increase the volume, what happens to our gases? Concentration goes down. So what happens to Q? Increases. Does that change things? Yeah, it does. How about if we add a catalyst? Good question. What does catalyst do? Addition of equilibrium. Does a catalyst change your equilibrium constant? No, it doesn't. What does it change?
Activation energy.
Changes activation energy, but it changes the forwards and backwards rate constants the same amount. It changes the energies of activation amount. So we don't change our equilibrium constant or our Q value by adding a catalyst. What does the catalyst do? It speeds it up, so all that happens is we get to equilibrium faster. So it's the same equilibrium, it looks the same, but we got there a lot faster. Really what we're doing here when we add more of, when we change the concentration, if something is at equilibrium, the rates forwards and the rates backwards are equal to each other, right? If we increase one of our starting material concentrations, what happens to the forward rate? It goes up, so the reaction moves forward until equilibrium catches up, but it's a new concentration. Okay, if we add more starting material, what happens to the rate of the reverse reaction? Initially, nothing, right? So what we end up doing is affecting the forward reaction and not the backwards reaction rates, which changes where we end up at equilibrium. Okay, how about temperature? But where the equilibrium is and where the reaction is going, forwards or backwards, depends on the difference between Q and K, right? Does temperature affect Q? No. Can it affect K? It can, because the equilibrium constant is the ratio of the forwards and backwards rate constants. And when we change the temperature, we're going to change those rate constants to different amounts. So we end up with a different numerical value of K. Okay, we can use Le Chatelier's principle to predict whether K is going to go up or go down. And this is how we do it. For a given reaction, like the one that we've looked at over and over, what do we know about the sign of delta H here? If delta H is negative, right? That means that something is happening with respect to heat when the reaction happens. What does it mean? Heat is given off, right? Okay. So if heat is given off and we raise the temperature, are we selectively adding pressure to the product or the reactant side? Here, let me draw it. Well, I knew the, makes it sound like I had to see what the answer is, doesn't it? You know the answer without looking at it. I just wanted to see what I had written on the slide. So this is what I want you to think about. I want you to say, if the sign of delta H tells you whether heat is taken into the reaction as if it were a starting material, or whether it's given off from the reaction as if it were a product. Okay, so if I have A plus B equals C, delta H is negative. What does that mean? Almost as if heat is given off as a product, right? In this case, if we raise the temperature, what will happen to the equilibrium? It will move to the left. So what will happen to your K value? So the equilibrium moves to the left. Are we making more product at equilibrium or less product at equilibrium? Less. So what will happen to the K value then?
Increase.
Then K goes down. But delta H is positive. That's like we're saying when the reaction happens, it has to take in heat from the surroundings, right? And take the heat energy from the surroundings and incorporate it into the potential energy of the molecules themselves as they form. Okay, in that case, if you raise the temperature, what's going to happen to that reaction? What side are you selectively pressing on if you raise the temperature? So the temperature goes up. What's going to happen to this reaction? Are we giving it more of what it needs to move forward? Yeah, so what's going to happen to how much product we get? We get more product, so what happens to the K value? Up. Okay, these ways of thinking about the reaction, you have to know what the sign of delta H is, right? And be given that like this. What if I showed you an energy diagram? Be able to take the sign of the delta H value from the energy diagram? Yeah, you can look at whether it's exothermic or endothermic, and that will tell you. Okay. Now, this tells you conceptually how do we make a prediction. But because this is Chem 106, we ask you to make predictions conceptually, and then we ask you to calculate exactly how much the change would be, right? So next time we're going to use equations that allow us to compare two different K values to different temperatures and figure out what will happen. Okay, here's a question for you. This reaction, A plus B goes to AB. What does that have to do with the pictures? What's A in the picture? What's B in the picture? What's AB in the picture? Then we say there's molecules that have the two colors, that's AB. What's blue? Okay, so this lump at the bottom is supposed to represent the solid. So this is starting with the red single balls, that's starting material A. This is product. We don't need to do this. Okay, what is the equilibrium constant represented by this picture? So the equilibrium constant is going to equal the number of molecules of AB divided by the number of molecules of A, right? What's the equilibrium constant for this picture? This one, right? Okay. If we raise the temperature to 500 Kelvin, when we change the temperature, we're going to change the equilibrium constant. What's the equilibrium constant that we get at the higher temperature? Okay, so you guys are saying 1, 2, 3, 4, 5, 6 of the product molecules divided by 2 of the starting material molecules. Equilibrium constant goes from 1 to 3 when we raise the temperature. Is this an endothermic or an exothermic reaction? Okay. If the K value goes up when we raise the temperature, that means an increase in temperature or adding more heat pushes the reaction forward. What happens when heat is taken into the starting materials as you move forward? So we're treating it as if heat were a reactant. Now, is heat actually considered a reactant? No, it's not a molecule, right? But we can think about it as if it's a reactant. So in this case, this reaction is endothermic. So can you see how if you can think about what does K mean, what's the effective temperature, track what's happening, you can actually get a lot of information. Now, could I show you those two pictures and say, draw me a possible energy diagram? Yeah. What would it look like? It would mean that the product molecules are higher in potential energy. Than the product. Okay, how does that really happen? We're going to have an exothermic reaction, right? Likely, this exothermic reaction has what kind of K value? Its equilibrium going to lie on the left or the right?
On the right.
It's going to lie on the right because the molecules would really rather be products, right? It's also going to lie on the right because the K value forward is much less than the equilibrium. I have to specify which K value I mean, right? What's bigger, the rate constant forward or backwards? Forward, which means my equilibrium constant, K equilibrium, is going to be greater than 1. If I raise the temperature, I'm going to raise both the forwards and backwards rate constants. Right? I'm going to raise the percentage of molecules over the energy barrier, going both forwards or backwards. What's it going to make the biggest difference to? Which of those steps, forwards or backwards, is hardest to achieve? So if I raise the temperature, it's going to make the biggest difference to that step. Okay, so if the temperature goes up and it makes the biggest difference to the backward step, what's going to increase more, my forwards or my reverse rate constants? Okay, so what does that do to my equilibrium constant? So the equilibrium constant is the rate constant forward divided by the rate constant reverse, right? If I raise the temperature, it has a bigger impact on the reverse reaction and the reverse rate constant. It's going to make the reverse rate constant bigger more than it makes the forward rate constant bigger. So what's going to happen to my equilibrium constant? Go down. Yeah. So Le Chatelier's principle is really connected back to what you already know about the energy diagram and kinetics and the relationship between kinetics and equilibrium. Okay, tell your neighbor all the things that can change equilibrium with a position of equilibrium.
About
Pressure.
That was my experiment.
And yeah, keeper.
that changes Q, which
Put my list. Concentration of starting materials, which you can express in terms of partial pressures. These really different ways to do things. Okay, what's missing here? Concentration of products or the partial pressures of products. There's only one more thing you can change. What is it? Yeah. Okay. When we change the concentrations, what are we changing, Q or K? Q. But then K stays the same, but you're still changing which one is bigger, Q or K. Okay. When we change temperature, what are we changing? Change Q when we change the temperature? Not in that moment. Yeah. Okay. So the whole point here is Q versus K tells you, are you at equilibrium yet or not? Do you have to move forwards to reach equilibrium, or do you have to move backwards to reach equilibrium? Once we know that, that tells us about delta G, that tells us about what's going to happen. That changes Q. If we change the partial pressure of the gases, what does that change? Q. These all change Q except temperature. What does it change? K. We only have to change one of them to change the difference between Q and K, which can push the reaction forwards or backwards. Okay, last 15 minutes. Think it through with your neighbor. you want is that all of this makes some nice cohesive sense, and you don't have to think it through. So okay, are you noticing? None of this is conceptually that difficult, except that you have to think through 6 or 7 things to get from one place to another, right? What's the way to counteract that difficulty? The way to counteract it is to have thought through it so many times that those connections flow naturally in your